Hello, everybody. This is going to be our last podcast of this chapter 13. And here we're talking about using a model to describe gases. And we're talking about the kinetic molecular theory. And sometimes you will see this abbreviated in certain texts or things that you look at as KMT. So the kinetic molecular theory are some basic assumptions, as you can see, about gases. And so we're just going to have a little discussion here, or I'm going to have a discussion, that gases are composed of tiny particles, and we look at them as small little hard spheres. Now, when we were talking about the model of the atom, and we were talking about the S sublevel specifically, we talked about the nucleus, and then we talked about that we have this region of electrons and where they travel. Again, we're not saying away from that. We're not saying that they're incredibly hard spheres, but they have to be dense enough that when they collide to each other, that they are creating some pressure. And so you can see in this box over here that there's a bunch of tiny particles, atoms and molecules, whether it's H2, which would be hydrogen, or O2, which is oxygen, or carbon dioxide, where you have a molecule. It doesn't matter. They are going to be colliding with each other, and they are small, tiny particles. They don't really take up any volume, and so this is based on the theory of ideal gases that we are putting into action. Particles are in constant random motion. Now you can see in this diagram that the particles are in random motion. They move in straight lines, 100 or 1,000 miles per hour. If you take a look at an oxygen molecule, a plain old oxygen molecule here in St. Paul would be able to get all the way to Detroit in 1 hour. So think about that. That's how fast they are moving. Now, obviously that doesn't happen because they are colliding with all sorts of things that are in our air, but they are fast moving. That's what helps with all the mixing that's going on, so our air remains uniform. They frequently collide with each other and the walls of the container. That's how we're getting our pressure. And the collisions are perfectly elastic. There's no energy lost. We talked about this in class already, so I was talking about like a rubber band. Remember, we talked about a rubber band. If you stretch it out and bring it in and stretch it out and bring it in, it's always going to go back to its same original shape as long as you don't go past its point of elasticity. But that is an elastic collision. And so here, even though they're colliding with each other, they are not gaining any or losing any energy. The other thing that you need to see here is that they are moving in straight line motions. So once they collide, they bounce off in a straight line motion. They'll hit another collision and they'll continue to collide. Now you can think about that if we were to create this volume smaller, as we did in Boyle's law, you can see that these particles, and I have the same number of particles, these particles are going to be moving in smaller areas, creating more and more pressure. The other thing you need to see is that there is no attractions. You're not seeing any dotted lines in here between any of the molecules. We are saying that there's no attraction or repulsion between any of these gases. They're just moving along and zipping along until they collide with someone else and like, okay, I'll move in another direction. There's not going to be any attractions there. Then the fifth point in the kinetic molecular theory says that the average kinetic energy of the gas particles is directly proportional. Remember, the word directly means that if one goes up, the other has to also go up, to the Kelvin temperature of the gas. So we are going to say that the average kinetic energy is proportional to temperature in Kelvin. And another way we need to know that kinetic energy is equal to 1/2 mass times the velocity squared. So we haven't talked about velocity to this point. Keep in mind that the measure of kinetic energy is temperature. And remember, we are talking about the vigor and the motion of these gas particles. When we take a look at temperature, if the temperature increases, you have to remember on that thermometer, it means those particles are peppering it even more, and so the kinetic energy is also going to increase. Well, if we are talking about this movement, if it makes sense to you that if I have a greater mass, I'm going to have greater kinetic energy. And so if I'm going to have greater mass, my velocity is going to be a little bit slower, and so my kinetic energy is going to be a little bit less. So whichever way you want to look at it, whether you're looking at a helium molecule or a hydrogen molecule that has a lot of velocity because its mass is very small, or with the little clip that I showed you about putting nitrogen in our tires, how the mass between nitrogen and oxygen is different, so this velocity would be different. So in general, you just need to know that the greater the mass, and we are talking about molar mass, so you can find its molecular weight on the periodic chart and add up all those different atoms that are there, is equal to, if I have greater mass, I'm also going to have greater kinetic energy. Okay, so this is kinetic molecular theory. Again, we could talk about, does this apply to all real gases, meaning the gases that we have? Well, if I have, again, low pressure and high temperature, most of these laws are going to hold to be true. And it's just an easier way that we can go ahead and make these assumptions so that we can continue to study the gases. Again, we have to make sure that, pressure plays a big part, the size of the container or the volume plays a big part, and temperature. Gases are greatly affected by all of these things. And one more time, if you think about a solid, if you think about your textbook, or you think about the computer that you're watching this on, I can't compress it, I can't make it smaller, the volume is not going to be changing. If I bring it into a high temperature or a low temperature, none of that is going to change, where gases are greatly affected by all of those parameters. All right, you are going to have 11 multiple choice questions or 15 multiple choice questions on your test, somewhere in between there. I would highly suggest that you really understand these laws to make sure that you can apply that if you change the pressure, what's going to happen to the volume of the gas. Well, if you increase the pressure, we know that that's going to go down. So you need to be able to apply all of these laws. Have a wonderful rock star night, and I will see you tomorrow.